So, very good evening to all of you. Welcome to IIT Bombay, and welcome to all the students and especially Vikram for inviting for this. I have formally made set of slides so that you come to know what activities we are doing. So, I'm a faculty member in the Department of Mechanical Engineering, and there is a lab called ICME and Materials Genome Lab that I chair in the department. I'm also part of Center for Machine Intelligence and Data Science. So I'm going to talk with you about the research that I do. So I'm a material scientist. I did my BTech in metallurgical engineering at IIT Roorkee back in 2002, and my research area has changed a lot. I have worked in the area of mechanics, in computational sciences, but it all started when I was a metallurgical engineer, and I realized that materials are very, very important, and I thought that I should share my experience. Especially because in India, when you choose branches, you choose based on which branch gives you the job. And it has been a bitter truth since I was an engineer. So we choose first computer science, then electronics, then electrical engineering. At some places, these branches are there. At some places, these branches are not. There are many other branches that probably IIT Bombay does not have. There are branches that IIT Delhi does not have. For example, we do not have probably a branch called textile engineering at IIT Bombay. We do not have pulp and paper and so on, right? However, if you go for higher studies and as you move on in your professional life and you join jobs, you realize that you cannot contain yourself in one branch. Your jobs, your profession calls out for multiple disciplines that you should know. And I realized when I was a scientist at first Max Planck and then at Los Alamos National Lab, that materials are something that you need. And I'll tell you that I realized that we should care a lot for materials more than we have cared in the past, because we ourselves are made of materials, right? We are materials. So that's what I'll talk about. I'll say that why should we care and why should we care more? Why do we care and why should we care more, right? I acknowledge IIT Bombay first of all with a lot of support, funding, and all my students of whom I will be showing some work here. So is there a pointer? No, it's fine. So I did my BTech, as I said, at IIT Roorkee. I worked as a quality control engineer in a very small company back then, but now it's a very large company in the area of oil and gas pipes. So they used to make pipes from steel plates. Steel plates are straight in the beginning and they are folded, and at the top they are joined using welding, right? So it's a very rough process. If someone offers you a job there, many of you would not like to join there because the shop floor is very dirty, right? But right now oil and gas is in demand parallel to EVs and everything else because it's energy, right? And when I joined the job, I was not really very interested because I was a quality control engineer and I was very, very young. And my job there, the way I was being used in the company was only one thing. It was a small company and they had to pass a lot of certifications like ISOs and API. API means American Petroleum Institution. And they used to show me that this is the change we have done over the past 5 years. We have hired an engineer from IIT. That's all. All I was doing was I was just signing their papers. I was giving certifications. That's it. But over the time, I realized that, even that dirty shop floor lacked a lot of things and there were things to improve. So I worked there for 2 years. Then I moved on to do research at University of British Columbia in Canada, because I realized that research was literally needed, and India back then, at least in those hardcore manufacturing plants, did not care about research because most of such companies, even now, they are profit-making companies. However, if you tell them that, using research, they can think about 10 years from now and they can make a lot of profits. For that, you need to yourself gain knowledge. You need to go global and see how other people are doing it and bring it back to India, right? With that, I took GRE. After I graduated, I did my master's at University of British Columbia. I was exposed to literally, the laureates, excellent people who were doing tons of material science and, mechanical engineering. And then from there, I started. I did my PhD at Washington State University, dropping another option at Ohio State because someone in the area in which I wanted to do PhD, father in that area was sitting there. and I went on to do a postdoc, which is called postdoctoral research that you do after your PhD. I spent a year at Max Planck in Germany, and then there I met another scientist. He said, why don't you join us in Los Alamos National Lab? And I went to USA, came back to USA again, and I did research with another top set of people in that area. Stayed there for 3 years, and many of you may not be knowing probably what is Los Alamos if you have not watched the movie called Oppenheimer. It's the place where the first atomic bomb was conceived, right? And I feel very happy that I visited the site, not for the reason that people lost life, but for the reason that it was conceived and tested there. I saw the site where the bomb was tested. It is called Trinity site. When you walk there, first of all, you cannot just go there. It is open only for 2 days a year, first Saturday of April and first Saturday of October, right? And you have to ask for permission. There is a lot of security, and there is nothing as such at the site because it's just barren land. Sand has converted to green big particles. It's called trinitrites. And when you go drive to that site, you'll see a lot of small shops. And those shops are actually selling fake trinitrites. They are just selling green glasses, which are not radioactive. They are just making money. But when you go to the site, you'll see a lot of green particles. So all that experience was really nice. And the way they show that site is they will show you pictures of 1 microsecond, 10 microsecond, 100 microseconds, 1 second, and so on. After the blast happened first time, there is a broken stage where the bomb was kept and so on. A lot of things are covered now under cement because they are still radioactive. You can see a lot of things. There is the thick shell where the bomb was kept and blasted. It was a great experience overall. For that matter, I also learned a lot of science there, top-notch science, which you see in journals like Nature and Science. You know, fundamental physics, fundamental chemistry, and that gave me another push. From Los Alamos, I was hired by a company called Mojumetal, and they were into, again, development of coatings for wear and corrosion, which are used in oil and gas industry, right? Another good experience that I was hired on the condition only if they sponsor my green card. I was clear by the time I finished my PhD that I had to come back to India, but I said that, you know, there is no other way I can stay here. If you want to keep me, you sponsor my green card and take me. So they literally sponsored my green card. In 3 months, I got the green card. I worked there for 1.5 years. I came back. And I'm not an exception, by the way. There are many faculty members here who have actually given up their green cards and, you know, even their citizenships, and they are here. So that's something about science. They are here because they want to do research. So we are here to, you know, bring that enthusiasm in you so that if there is little bit of science that you want to do, this is the place. You are at the right place right now, right? So I joined IIT Bombay in December 2015, and this place literally gives you absolute freedom to do what you want, right? It doesn't matter in which branch you are as a faculty member. Of course, you have to teach. As a student, you have to study because you are in a particular branch. But beyond that, you'll get a lot of opportunities to collaborate with faculty members and other students in other departments. There are centers which are interdisciplinary, which bring a lot of faculty members from other departments, right? So there is no lack of opportunities here. The topic that I wanted to talk with you is here. So, you know, materials have evolved since centuries, you know, and ages. So, for example, it started with stone ages because the material that was absolutely available around you was stone, literally. You don't have to go and fetch it. You don't have to extract it. No heat or chemical reactions are needed. Just grab and use, right? And that's why it started there. And then people realized that, you know, you can heat the rocks and minerals, you can extract metals. And as they learned more and more about it, Iron Age, because they learned how to get iron, how to get rubber and plastics from plants and so on. And things kept changing, you know, as they learned the science of extracting materials from various sources. Various materials have came in. And as I say that materials are the mirror of society, you know. Right now we talk about molecular age because we know how to manipulate molecules. We can generate new molecules, right? We can design literally. We don't have to live with what we have been given. So right now we are living in this age called intelligent materials. That does not just mean that we have created those materials intelligently, but also those materials themselves are intelligent, right? The molecules that we make, they can by themselves walk, right? There are molecules that you can introduce in the body and they know exactly which other molecules to attack and get rid of the diseases, right? Drug delivery materials and so on. So as time has passed, various materials are of importance. For example, in the beginning, I told you stones were important, polymers were important. They were used more because they were more available. As we learned how to develop metals, there were super alloys because they had more exotic properties. They could be used at higher temperatures and more exotic extreme conditions. Right now, we live in a world where we have a lot of metals. We have developed a lot of metals. We are living in a world of more or less in a balance, right? We have sufficient polymers and composites and so on. Composites are materials where you mix a lot of different materials, right? Those are composites, right? So we are living in a world of engineered materials, not the pure materials right now. There are some more examples. We have tools that were used in Stone Age on the left side. We have utensils from Stone Age, very famous iron pillar, which is also called Ashoka pillar, Qutub Minar, right? All these were not just made because someone wanted to make things beautiful, right? They were made because the whole science of constructing tough, strong, durable materials and maybe for some other purposes could be made, right? Paper itself, ancient paper itself is an example of what materials are, right? You take a lot of effort before you choose on what to write. You cannot write on anything and with what to write, right? What type of pen should be used, what type of ink should be used, and so on. So this is the evolution, starting from how to crawl. We are here. We have, touch screens which are foldable, right? In next model of Apple, Samsung has already released, by the way, a foldable screen. Apple, next version of Apple phone will be foldable Apple phone. We have exotic materials using which you can trap solar energy like perovskite materials. We have electric vehicles, right? It is not just a battery car. It is not just a battery vehicle. There are tons of other things that you have to think about. For example, when you put battery in a vehicle, the vehicle becomes very heavy because batteries are not, I don't know how many of you actually have taken batteries in your hand and weigh them, right? They are very, very heavy. So you put 50 of those, your car becomes heavy. So now you have to get rid of weight from somewhere else. So you change the structure, you change the probably chassis, you change the front panel, you change the car doors and so on, right? So a lot of thinking has to go in. And then the battery cannot drive probably the old engine. You have to come up with another engine. So you think about from where will you get copper wire? How will you draw it, right? How to solidify the copper wire, how to get a pure copper and so on. So a lot of science goes into this, right? Light materials like micro lattices are again like exotic innovation in terms of material science. Small computers as small as probably smaller than a grain of rice, right? Atom bomb is an exotic example of materials because before you make atom bomb, you have to think about how much critical mass of uranium and plutonium is needed. First of all, whether plutonium is needed or not, right? So if you have seen the movie, you know what went into this. There are strategic and futuristic applications of material, for example, thermal and nuclear power, oil and gas, railways and other infrastructure, for example, bridges, magnets and rare earth using which permanent magnets are made are again something which are needed by every country now because these magnets are used in everything that we are using for power generation and for defense. For example, I don't know if you know, the aircraft that are used for dropping bombs and missiles, they use these permanent magnets for switches. You need magnetic switches for closing that hook using which the missiles are dropped. And these materials right now are not in India. They are imported. So these are strategic materials that India wants to make, right? Microelectronics like GPUs and chips, and precious metals like gold, platinum, and so on. And like I said in the beginning, that we should care even more because we ourselves are materials. Earlier people used to wonder what will happen if you lose a limb, if you lose your finger, hand, and so on. But now we have invented materials using which you can create synthetic organs, right? We have created materials using which you can have implants of your teeth, your thighs, thigh bones, and so on. So all these can be either 3D printed or they can be created otherwise, right? So it's matter of only cost these days. They are not always very cheap. They are expensive still, but we are moving in the right direction. All this has been possible because people realize that at the bottom of everything, all of this, there are materials that we should care for. You cannot generate the next generation technology. You cannot chase it unless you know how to create the material that is needed for that technology. You think about next generation iPhone, next generation high power chip or GPU or anything. You cannot go for it unless you generate the next generation material. That's the bitter truth, right? Like I said, we have molecular machines that are used for drug discovery. So what do I do in all this? Like, how do I contribute, right? So my lab works in the area of accelerated material design. I started with doing classical material science experiments. I went more into computational sciences. So I do a lot of computationals. Computations, I basically understand how metals deform, how do they fracture, and how to get better material. If some metal is fractured, how to get next generation metal which is not fracturing as much, right? So overall, we care about what process to be chosen, and if I choose a process, what will be the structure of the metal or any material. If that structure is given, what will be the property of that material. And all this is fine because this is the design, but let's take it to the lab and test it, how it is going to perform. If it does not perform, take it through next cycle of improvement and keep doing it unless you get the best that you want, right? So earlier, all this exercise used to be done in lab, sometimes using classical physics methods, computational methods, but it used to take a lot of time. We have, like many others in the Western countries, have integrated it with AI and ML. We have done that also, and now our methods are really, really fast. We can actually simulate anything that you see in the lab or in industry. We can simulate deformation of any kind, of any material. We can simulate fracture. You have a crack and you load it and how the crack propagates. And we can simulate if there is a pit and there is some liquid media that creates those pits or accelerate those pits. How much time will it take for a crack to go from the one notch to the other side, right? We can do all of this. And we do not use softwares that are bought in markets. We create those programs. We program a lot. We program in Fortran. It's ancient language, but still is used in physics. It's the fastest, one of the fastest, right? C++ is the fastest. Fortran is somewhere near. We use a lot of that. We use a lot of Python for machine learning, for generating materials which do not exist now. We have created about 100 alloys which are being tested in various labs, right? We have digitally created them. We know the compositions, we know the processes, and we have given the recipes that this is the most likely recipe, try it out. So those are being tested in several of the national labs in India right now. And all that is done in these computational facilities. This is a facility that I manage in the department. This is a 14 node cluster plus several GPUs and plus a very large data cloud. So the data cloud that I have is a 60 terabyte data cloud, and it has gathered data of about 8 years of our research. Plus there is one more copy over the internet, right? And these 14 nodes that I have about 400 cores. And those are not the cores that we use in laptop. Those are exotic high performance cores with really huge RAMs like 60 GB and so on, right? So all of that I'm showing you is not possible with this, and this is not possible unless you design the next generation. The system that I'm using is already 8 years old, right? So this is the last slide. you. So I hope no one is getting bored. This is my last slide. So the research has been picked up with lot of media and agencies and government agencies. We have published edited books. There are several articles that you'll find on IIT Bombay website. There is an article that was published in ET Auto. This is my research. There is a media agency called ResearchNet. They also published my research that how to accelerate material development using AI. That's a cover article on in a journal, and so on. If you have any questions, I'll be happy to answer either now or later. Thank you so much.
Good evening. Can you hear me? Yeah, I am Shubhimal from Civil Engineering Department. As well, I am heading. There is an interdisciplinary center which is climate studies. So I'll start with in 1999. There was a cyclone that took place. The name of the cyclone was super cyclone. The wind speed was around 260 km/h, and because of that, 15,000 people died. Okay, and for I think for a couple of months, the specific region was completely detached from the outer world, and there was a significant and huge loss. In 2020, exactly a similar magnitude cyclone took place in West Bengal. It was Amphan in 2020, and exactly the maximum wind speed was 260 km/h. The intensity was very similar, but only 100 people died. Do you know why? That is because over the last 20 years, a silent revolution in science took place. And that is in climate science, that is in weather science. And because of which was unpredictable, the tropical cyclones, whatever is happening over Indian region, over the tropical region is very difficult to predict, which is much easier in the European countries or US because they are in extratropical region. But whatever is happening over the tropical region, that has a very low predictability. But still, with that low predictability, the scientists could forecast the cyclones with exact location of landfall and with exact timing. And that's the revolution that took place, but it was unattended somehow. It never got an attention like Chandrayaan, but it actually saved a lot of people's lives. And that's what is climate science. So, and this is what is very important. We have to understand why is this important, because over the last few decades, the climate extremes have increased significantly. And why has it increased significantly? Because from 1950, there was an industrial revolution, even before that. And globally, mostly the developed countries, the global north countries, have used fossil fuel extensively. And because of which we have generated a huge carbon dioxide in the atmosphere, and that carbon dioxide has a huge residence time in the atmosphere. And because of carbon dioxide, there is an extremes. There is an increase in temperature, global temperature, and which is around 1.5 degrees centigrade. Soon we will be reaching 2 degrees centigrade warming, and that has significant impact simply because if you consider just 1 degree centigrade warming, that results into 7% increase in extreme rainfall. So that sort of increase we are actually talking about. And it is shown that over last 50 or 60 years, the kind of heat wave which you used to get once in 50 years that are happening now 40 times in 50 years. So that sort of increase we are seeing, and that has significant impact on every sector of life, being it a water sector, being it health sector, being it energy sector, being it infrastructure, being it transport. At each and every sector, it is actually affecting. So now comes the first thing is that we have to understand how is it increasing, what sort of carbon dioxide concentration may lead to increase in extremes, and how can we forecast it better. And that's known as early warning. That's the first thing, where a lot of development has been happening, and because of which we can see that in 2021, the Nobel Prize in Physics goes to climate scientist. Manabe and Hasselmann got this Nobel Prize, 2021 Nobel Prize in Physics, which is because of their contributions in climate modeling. Now the second thing is that what are the solutions? So we have to think about solutions, and specifically for a country like India or any global south countries are actually in trouble, because the global north countries, they have, like if you consider US or European countries, they have made a lot of development and they have polluted our atmosphere. They have actually done the mess. Now we all are in trouble and we have to find a solution. We have to reduce the greenhouse gas emissions. We have to take care of the carbon dioxide which is there in the atmosphere. But at the same time, we have to develop. We have to make a lot of development. If we cannot develop, then people who are suffering from poverty, if they are under climate stress because of, let's say, agricultural activities, they are losing, I mean, there is a crop yield loss or anything, they are committing suicide. So we have to take care of their development, and we have to take care of their development. We need energy. But how can we get the energy? Because we cannot really use the fossil fuel. If we just use fossil fuel, then we will be as criminals as those Western countries. So we should know that. So our challenge is that we have to make the development, we have to improve our energy situation, but without fossil fuels. That means we have to do mitigation. So there are two things in climate. Of course, the first one is climate science, which I briefly mentioned. The other two challenges are climate adaptation and climate mitigation. Let us try to understand what does it mean by climate adaptation. Let's say from tomorrow, all the countries stop emitting greenhouse gases. Still, whatever carbon dioxide that is there in atmosphere, it will affect at least for next 40 years with this kind of extremes which is happening now. So what we have to do, we have to improve our early warning and we have to improve our adaptive capacity. What does it mean by adaptive capacity? Let's say a city, if you know that some flooding has happened in Delhi 2 days back, flooding happened in Mumbai a week back, and a lot of flooding and flooding also happened in Pune a few days back. So the city drainage system is unable to take care of the increased extreme rainfall, right? So that is the adaptation gap. So what we have to do, we have to improve our drainage system. And if we have to improve our drainage system, we have to understand that in next 10 years or 20 years time, how much extreme rainfall increase we are expecting, and then accordingly we have to improve our drainage system. So in that way, we have to improve our adaptive capacity. So let's say tomorrow all the greenhouse gas emission is stopped, but still we'll suffer, and because of which we have to make ourselves ready. Interestingly, the global north countries are ready because they have money. We have problems. So we have to make ourselves ready, and that needs energy and so on. And if you need energy and so on, then what we have to do, we have to make it green. And when we have to make it green, we have to go for green energy. We have to go for solar energy, we have to go for wind energy, we have to go for hydropower, and at the same time we have to go for capturing the carbon dioxide which is there in the atmosphere. So these sort of technologies we have to develop, but not at the cost of development. So we have to continue the development with climate mitigation. So in a country like ours, our challenges are more compared to any of the Western countries, where we have to go for climate adaptation as well we have to go for climate mitigation. And that's what climate studies do. Yeah. And also, while doing this climate adaptation and mitigation, we do a lot of nice experiments. Let's say if you are in Mumbai, and if you are going from IIT Bombay to Navi Mumbai, if you go, in some regions you will find heavy rainfall is happening, in some regions almost dry condition, again heavy rainfall and so on. In 2-3 kilometers the rainfall patterns are changing. So we do experiments, we do numerical experiments to understand why these things are changing. Can we include them in a predictive model? Let's say if you are thinking about, we know about health, right? Health is actually connected to weather condition and seasons. We know our parents used to say that, okay, be careful, now season is changing, so we may get influenza or we may get cold, right? We always say that. But let's say if you are considering there are certain villages which are at remote condition, and there, if you know there is a chance of influenza outbreak, what you have to do? You have to do a lot of resource management. You have to make sure that health resources reach there well in advance. And if you have to do that, you have to go for better health prediction. And since health is related to climate, so you should have to make that connection. You should have a very good prediction system that should be connected to health system, and then come up with resource management in health using climate and health concepts. So which are Government of Maharashtra now they are doing. So there are a lot of if you're talking about energy sector, of course we are talking about green energy. But you know, for green energy, there is one of the major problem is known as intermittency. What does it mean? That means, you know, you're talking about solar energy, but suddenly you are finding a cloudy sky. So what will happen? Your radiation will not come, and your solar energy, there will be a drop. And when there is a drop in the energy availability and energy demand is increasing, then what will happen? You will be in trouble. You cannot manage energy. So you should forecast this intermittency of green energy. So anything you are talking about, any scientific development, any technological development, that has to be climate resilient, and we have to make every sector of scientific and technological development weather smart and climate ready. And that's what we do. So please send us emails if you are interested. We'll be very happy to work with you. In fact, we are starting from next year onwards, we are starting an undergraduate summer project program on climate and weather. And our donors are actually supporting, our alums are actually supporting for this. So we want all of you to understand the importance of climate, and whatever scientific development, whatever technological development you are doing, please make sure that that should be weather smart and climate ready. Then only that will be sustainable and people will buy that. Thank you.
Can you all hear me now? Well, you could hear me anyway. So I'm Ruchi Anand, and we are back. We are from materials to climate to chemistry. And I think most of you think of chemistry as mixing chemicals or writing organic reactions. Pretty much that is where the thought of chemistry lies. I want to tell you a little bit about myself too. I thought I was hearing the previous speaker, and I thought that maybe I can tell you how I decided, you know, and was it worth being a chemistry professor now that I am, right? So actually, I grew up in a small, not a small town anymore, Dehradun, right? That was where I grew up, and you know, my class was like those, you know, those all of you must have come from the same background, super class. We were a class of 50 and 32 of them made it through IIT when I was studying. But the problem was when I was in that super class, like all of you must be feeling happy as you're here, I realized that I did not want to do engineering at all, right? And I did not want to become a doctor because I didn't want to cut things, you know. I didn't want to be, you know, they used to make us do these experiments with a frog, and I would not be able to tell where's the heart, where is anything. And I'm like, I love biology. You know, they say women love biology, but I love biology, but I couldn't do those. I was like, man, all these toads are dying under my, you know, in 10th class. So I took up computer science and entered that class. And but my father was a scientist too, so I also wanted to be a scientist. And the great thing about it, there are a lot of women here. I'm also a woman. So that gives me an edge, right? I can do whatever I want because I'm going to get married, right? I don't have to worry about, you know, clearing IIT or doing anything. At least that's what half the world thought. So I decided to do whatever I wanted to. Okay. So I ended up doing, I got interested in, actually I was interested in more biochemistry, but I ended up doing a lot of physical chemistry because my father never thought that, my father was a chemical engineer, is a chemical engineer, I would say. He always thought that, you know, we should, that exact sciences are better. So I was just waiting for an opportunity to be able to do a different kind of thing. So I did I went to Miranda House for my undergraduate, and then I went to IIT Kanpur for my master's, and I did project in quantum chemistry at that time. So, you know, that's the subject maybe you do not learn when you are studying for JEE, but that's what they keep teaching you when you are going to be studying chemistry and physics. So, but then my heart didn't lie there. I went to Cornell for my PhD. And I really wanted to do PhD because I was interested in research. And it's there that I shifted from quantum chemistry to actually doing enzymes, to solving structures of enzymes. So there's a lot of math in it. And the first Nobel Prize actually went in protein structure determination to a mathematician. He was from the Hoffman Institute in Buffalo, and we actually knew him while we were working on it. So I started solving protein structures, and it turns out over the years you will see large number of Nobel Prizes have gone to structure determination. Till very recently, in 2017, we got the cryo-electron microscopy. Richard Henderson, he's in Oxford, he got the Nobel Prize along with 2 other people. At least, and then there was a prize a few years back for Venki Ramakrishnan. I don't know whether any of you have heard of him. He's an Indian who actually grew up here and then went for studies outside. So what does that help us do? So, and what do I do now? Right? So I came back and started, I went to, did my postdoc, like, went to Cornell, MIT, and I was there for a while in UPenn too. And I started doing more cancer-related research. But when I came back here, I realized, the amount of money I needed to do my research that I was doing there, these were not the problems I wanted to stick with. And there are 2 problems we work on, and I'm going to talk about the first one. Antibiotic resistance is what we work on. All of you, how many of you have taken antibiotics? Do you know name of any one antibiotic that comes to your mind? Penicillin. How was penicillin discovered? Does anybody know? By accident. What about streptomycin? Does anybody have heard of streptomycin? Erythromycin? So we work on erythromycin and streptomycin. The question that we are trying to answer is, how do bugs become resistant to antibiotics, right? So that is the question. And it's not a chemistry problem. It's not a biology problem. It's a science problem, okay? And we do a lot of other things to answer it. Do you know how streptomycin is produced? Anybody? From a bacteria, streptomycin. So the first question we asked was, the bacteria which produces streptomycin, how come it doesn't die of its own antibiotic? That is because it has resistance mechanisms to save itself from the antibiotic it produces. And that's how you're getting multi-drug resistance. Many of these bacteria which produce the antibiotic, which we wanted to use, are the bacteria who also give other bacteria resistance. They will be like, hey, can I take your resistance mechanism because, I don't want to die. It's better the human dies, right? It's a race. It's a race. So that's what we study now. We try to understand, can we be ahead of the race a little bit? We can never win. We can never win. Evolution is something that you cannot fight. But we have to be ahead of the race because we want to live too. So as a result, when we do these kind of research, we try to come up with understanding why and how this resistance mechanism is functioning. We work with enzymes, we work with new molecules. So a lot of chemistry goes in our department. There are a lot of chemists, like, for example, we have chemists who work in sugar chemistry. We have chemists who work in understanding catalysis in field like that. And in our lab, we collaborate with lots of chemists, some from IIT, some from outside IIT. And the main question that we are then trying to answer is this particular one. Can we come up with newer antibiotics, which is very difficult actually, that will bypass resistance? There are 2 ways. Either you add another molecule such that you shut off the mechanism in some way. I would love to describe it more in a much more, if you guys want to know more about it, we can have a little bit more scientific talk then. But mostly we try to understand if we can, many times what happens is the old antibiotics stop working. So can we give a combination, some kind of molecule such that the old antibiotics start working again? Or can we develop completely new antibiotics by developing new molecules that bypass this resistance mechanisms by knowing what the resistance mechanisms are? So this is one of the major focuses of work in our laboratory, and it is a field which combines lots of other fields because we solve a lot of structures. And to do that, we have set up a cryo-electron microscopy facility over here. And that cryo-electron microscopy facility actually, costs around 40 crores. So that's a lot of money that we spent in trying to understand structures. But what it does is it gives you an atomic level picture of complicated molecules such as the ribosome, which produces all enzymes in our cell membranes, how cells are organized, information like that. So we can actually tackle organisms based on atomic pictures. So protein crystallography was also atomic picture. Cryo-electron microscopy, which is the future of the field of determining structures is also something in which you get atomic pictures. Like we take pictures of us, we take pictures of cells, we take pictures of proteins which are at atomic level, right? You can see sometimes as close to carbon-carbon bond. What is a carbon-carbon bond? 1.54 angstroms. So you can see molecules. You can't see, so you can see, get really bond-wise information, and then from there you can try to understand what's happening, what type of enzymes are working. So this is what we are trying to do as far as our group is concerned. But chemistry department, like I was telling you, unexpectedly not mixing, not doing what you think we are doing, because that's the perception. And if you see some movies, they will also show that, because that's the perception that remains. Many of our colleagues work in materials, advanced materials, similar to what was just shown. Many of our colleagues actually work in catalysis, where they try to, enhance processes. They work with natural product chemistry. They want to make new kind of, many of the natural products are used as drugs. So they actually try to enhance those. Many of them completely work with spectroscopy techniques to probe things, right? So they're completely very different. Many of them work with machine learning and ML used for predicting chemical reactions. So the field of chemistry is actually very different from what most likely you envision, because what it was in 1950s or 40s is not what it is today. So when you are thinking of the chemistry department, go to our webpage, see all the different kind of things we do, which is not at all what you think is what you were expecting. Okay, so with that, I leave you, and I know we've taken a lot of your time, but thank you for listening. Bye.
Okay, so I'll actually give a very short introduction about myself. I am one of the, as far as I know, only 4 professors in IIT Bombay who are a BTech. Well, I'm the only professor in IIT Bombay who's a BTech, MDes and PhD from IIT Bombay. And only one of 4 professors who have like their undergraduate, masters and PhD from IIT Bombay. Okay, so only one of 4 as far as I know. Okay, so, and if anybody can tell the other 3 names, then maybe you get a virtual chocolate. Okay, this is kind of blown up, but hopefully this will show correctly. Lovely. Okay, so I'm going to invite all of you. So I come from the IDC School of Design. I'm currently a professor there, and I invite many of you who are not from IDC to come and design for and with emergent users. And you might notice 2 words there, for and with, and I'll kind of let you figure that out. So this is a 10-minute compressed version of about an 80-minute lecture. So I'm not going to give the whole lecture, but I'm going to actually try to leave you some ideas about what is emergent users. I'm actually going to spend most of my time talking about it. And about the last 90 seconds, I'm going to talk about 3 projects just as an example, okay? So that you can get an idea कि भैया कुछ कर सकते हैं, okay? So what are emergent users, okay? So we can look at many technologies, but here is just the internet. So in March 2014, okay, about 10 years ago, we had 2.9 billion or if you like crores, then 293 crore internet users in the world. What is the world population? Fantastic. So that's like the y-axis over there. I'm sorry the slide is not very clear. That is because there is this light over here, which I tried to look at whether there is a switch somewhere that I can switch off. But I will send you the slides. At the end of it, you can take the slides. Okay. So 2.9 billion internet users, March 2014. By April 2024, just before you were giving JEE, the number had gone to 5.4 billion. Okay. So, and that works to about 476 new users per minute for the last 10 years in the world. 400, like the last, whatever, 3-4 minutes that I have been speaking, 1,600 people started using the internet for the first time in their lives. Okay, now you guys probably don't remember. Anybody remembers the first time you used the internet in your life? Who remembers? Raise your hand. Can't be, right? You guys are too young. Right. I remember the first day that we used a TV, and I'm sure Sapatwazan here remembers. Right. So that's the second half of the world that we design for, roughly speaking, and that's what we call emergent users. Okay, I'm going to show you a picture of India here. So that was the world picture, but I actually have a slightly more detailed picture of India. So that's the population of India, and that's the number of mobile phones in India from 1990 till 2024. Well, the population is projected to grow based on whatever Google thinks will happen. Okay, so this is based on Google's approximate data. So that's the number of landlines though. That's the number of internet users in India. Okay, so currently about 88-89 crores. Okay, that's the number of smartphones ever sold in India. So that's the number of mobile phones, and of course, smartphones die quickly. So who has the oldest smartphone in the room? Anybody has a very old smartphone? Anybody has a very old smartphone? No, all of you got new smartphones when you came to IIT Bombay. Right? Yeah, so I have a 4-year-old smartphone. Just after the pandemic I bought. Okay, because I needed a phone at that time. I have only 3 minutes left for 8 minutes. Okay, so smartphones don't die, right? They don't live forever. So we are, on an average, we find that smartphones live for about 5 years. So we are tracking 5-year-old smartphones, and they are kind of peaking off a little bit now. Okay, so that's those two numbers are not very far from each other. They are about 80 to 90 crore in that range. So that's the number of internet users in India as of now. Okay. Yeah, so that's sort of one picture I wanted to give you, but I'll actually superimpose this with another picture. Can anybody take a guess how many graduates we might have in the country? A good guess. 10 lakh, 1 crore. Okay, so 2011 census put about 8 or 9 crore graduates in India. About 6.5% was the estimate for 2011 census. We haven't had census in 21, so I don't have a good estimate after that. But I was looking at the election polls recently, and that gave me a pretty surprising number. So the current estimated number of graduates in India is 24 crores. Okay, and we can have a long political discussion about that. But so that works to about 16% of the population. That's been a huge growth in the number of graduates in the country, from about maybe 6.5% in 2011 to about 16%. So that's a huge growth. I mean, if those who are in education, all my professor colleagues here will really appreciate this number. Okay. Similarly, this is the HSC diploma. This is the metric. This is the middle school, and there is I'm just extrapolating because the polls didn't give any middle school number here. So this is a dotted line. I mean, everything is a dotted line, really speaking. And then primary school similarly, and that's the literacy line. So 57% illiterates when I was a student here, doing my MDes in 1990. Okay, 35% illiterates in 2001 census, 27% illiterates in 2011 census. The current estimate is about 10%. Okay, so that's sort of India. It gives you a picture of India, and I wanted everybody in this room to go back with a picture of India, at least, if not anything else. Okay, so in our lab, okay, so something came. Okay, in our lab, we don't look at people who are HSC diploma and upwards. Okay, so those are all, I mean, we think that whatever, Instagram is good enough for them, basically, right? So we look at, first group we look at is what we call the non-English literate, roughly middle school, a little bit, some of them till 10th, educated till 10th standard, some of them till primary school maybe. The people who are less than primary school educated, we call them the barely literate, and of course there is the illiterate. So that's 8 minutes. So this is the time to show the 3 projects that I wanted to kind of highlight, one in each of these groups. Okay, so I'll start with the illiterate group. Okay, and I'm going to show you some work of a student who did this back in 2010. The technology is a little old now, Okay, but you can take a look at it and hopefully this will run. Yeah. So she was trying to support adult literacy classes with tangible letter forms. Okay, so she made some tangible letter forms and tried to support literacy classes. Okay, so she went and put this out, and the idea, well, there is of course you need a teacher and the teacher will help and so on, but what you really also need is someone to, so these students can learn on their own a little bit. Okay, so she created this, that technology didn't work very well, so she changed it to OCR based technology, and here is an adult illiterate, that's the sound. Right, so she explores, this is meant for helping people to explore and figure out things on their own. Okay, I'm going to skip, I'll give you the slide. Okay, more work, I'm going to skip this also. I want to show you one example of work for barely literate. So this is again fairly old work, 2009. So if you have a neighbor that you know and have their, okay, think about your roommate. Do you have their phone number? Look up their phone number, but without typing on your phone. Can you? Try. Look up your roommate's room number without typing on your phone. See if you can do it. Okay, it's a challenge because many people cannot type in English, in Indian languages, any of the languages. Okay, so here is a solution that we created for feature phones back in 2009. So it's a colored diary where each number represents a page, represents a color. So that's the red page. The filled ones have numbers in them, and the empty ones, the hollow ones, where you can add a number. Okay, so it's a contact book which is a kind of, which is using colors and icons basically without typing. Okay, so have you figured out how to figure out your roommate's name without typing? So here is one way. Okay, the last quick example, and I'll stop, is the non-English literate people. These guys are literate, okay, and we want solutions. So raise your hand if you typed anything today. Everybody. Now keep your hands raised if you typed something in your mother tongue. This happens only in India. Doesn't happen anywhere in the world. Okay. So very good. Thank you very much. So probably you typed also on your smartphones, right? So keep your hand up if you actually typed on a desktop computer in your mother tongue. On the desktop computer, well done. Very, very rare. 1 out of, so I think. Okay. So this is a project to which more than 100 people have contributed already. Now I have run out of space. So like, and you are welcome to join. And there are many projects over here. Text input in our own languages. We don't have text input in our own languages, and that's a problem that we need to work on. Okay. Nobody else is going to come and work for us. We have to create the solutions ourselves. Okay. So this is a classic example. There was a nice mural set up in IDC once. It was very delicate, so they wanted to put up a sign. The English sign is typed, the Hindi one is not. So this is a classic thing. You've seen it everywhere, right? Right. So we came up with a whole series of, we have many projects. Okay, some 27 projects, more than 100 people have worked on it. But one of them is this product called Swara Chakra. This is something that we launched in 2013. So this one is the Hindi version. We have in 12 Indian languages. So it actually allows you to type in 12 Indian languages. So this was Hindi. We have Marathi and Bengali. We have, come on. Gujarati, Malayalam and Assamese. Assamese, Bengali are different, by the way. Anybody from Assam? Yep, Assamese and Bengali are different. Come on, I want to just show all 12. Kannada, Telugu and Odia. And come on. And Konkani, Punjabi and Tamil. Notice the Tamil, it's very different. Okay, so So we have these, of course, and we have done several studies. I'm not going to go into those. We have compared this keyboard with many other keyboards and so on, and we've done better than most others in systematic studies. Unfortunately, well, we put it out in 2013, and then we probably have some 80 lakh plus downloads, and then we kind of, but we don't even really, I mean, we are not a startup, right? I mean, so I'm sorry if you're going to give a startup talk here after some time. But so Google has been removing our keyboard. So if you know Android programming, for example, you can volunteer and maintain this. Basically, you have to just tick some boxes inside Google and say, then they give whatever. But if you want to download any of these, they are available on my website. You can look them up. Okay, so we've done some studies. I'm going to skip some of these slides. Okay, so thank you very much. I wanted to kind of tell you that many solutions, many technology-based solutions for a large number of emergent users are now possible. I just shown you 3, but if I have more time, I can show you more. And I wanted to give you this picture. Sometimes we design for emergent users and sometimes we design with them, and sometimes something in between. So many solutions. I would like to share more. They are not a monolith. We have researchers understanding how they adapt to technology and so on. So one of the models that we created. And we are looking for collaborators, and that's where you will find the, so tiny, Enthuse 24 on tiny URL. You guys had left it for me. Thank you very much.
Good evening, everyone. A warm welcome to IIT Bombay. Are you feeling enthused? Enthused enough? Not so much. Few head shakes left to right, few head shakes up and down. Don't worry, I'm the last speaker, and I believe after that students have a very short, engaging demo for you, if I'm right, right? Correct. So, and that's the only thing between you and the long day and tempting dinner, hopefully. So, I'm Amber Srivastav. I am Associate Professor with Mechanical Engineering Department. I don't have much content on here on myself, so I'll quickly speak for half a minute. I did my undergrad in marine engineering, and then I worked on ships for 4 years, so I was a practicing engineer. After that, I moved for graduate school. I was in the States for master's and PhD. I worked there in corporate R&D for a while, and then moved to India and became a faculty here. Since then, I have been part of mechanical engineering department, and I'm part of the manufacturing group in particular, where we do a lot of interesting stuff. So the rest of 7-8 minutes, I'm going to utilize to walk you through over some of the very engaging, enticing features of manufacturing, what are current trends, what are some of the future trends, and just one single slide on what we do, particularly in my lab. Okay. So that being said, there is a very textbook definition of mechanical engineering, which you all guys are going to, or a lot of you are going to encounter. Anything where we need to design, produce, and operate machinery in particular comes under the umbrella of mechanical engineering. And there we have some of the particular core areas. Mechanical engineering is a very broad area. First 3 topics, mechanics, dynamics, controls, put together constitute design. A lot of that gets into controls, evolves into robotics, so forth and so on. The next set of subjects, thermodynamics, fluids, heat transfer, lead to what the area is known as thermal fluids. And what is of interest to me comes at the bottom, which is manufacturing processes and systems, materials and materials processing. So that's where the manufacturing comes into picture. So all in all, anyone who is enrolling into mechanical engineering, the curriculum is going to take you through a lot of this. And a lot of people like me are going to engage with you, particularly in this bottom tier. Okay. So that being said, manufacturing. What is manufacturing? Manufacturing is an enabling technology. Any thought which comes to your mind, you do all the calculations, a lot of which you have learned in your previous years, you will put it to use, come up with the ideas, know how you want thing to be. But from your mind, from your computer, it has to become a reality. It has to come into 3 dimensions in front of you. And that's enabling technology. The technology which enables you to do that is manufacturing. Without this critical step of manufacturing it, to the way you have thought of it, to the way you have designed it, it will always remain in books, it will always remain in your mind, and it will always remain in your desktops. Does that make sense? So this is how manufacturing helps us. And now beyond this enabling nature of manufacturing technology or science, it also acts as backbone of the economy because it leads to a whole lot of jobs which it creates. So a lot of people who are actively working and contributing to manufacturing research are not only creating the intellectual property, but also enabling a lot of future employment by opening new venues where people can come, join you, work on the path which you have developed and earn their livelihoods. That being said, it also supports a lot of innovation. A lot of studies in some of the previous of the speakers mentioned in the area of biology and chemistry and biomechanics are happening because mechanical engineers, particularly manufacturing researchers, have enabled a lot of instruments which allow them to see things at a smaller scale, which allow them to launch projectiles from a high enough velocity to reach outer spaces, so forth and so on. So that being said, without getting too much into the history of all of this, all of us would have heard of Industrial Revolution. Anything around us usually has some impact of technologies which were developed back then, and a lot of development have taken since then. What we do here at IIT Bombay and many other such institutes, the current trends and future, which I will walk you through a few, is to keep on continuing that thread of development which started back then. Manufacturing research, or some people would like to call what drives manufacturing research, make more, make fast, make better, and be able to make more complex shapes, parts, products around us. All of this is done with the true, thought of what engineering is for, to make your life more and more convenient. Okay, that's why engineers exist. Some of the current trends very quickly, and all of these areas where there are a lot of people who are working at IIT Bombay, at my department, and colleagues from many other departments here. Automation and robotics. How many of you have heard of robotics before? Great. Now, what robotics would do for manufacturing? That's a good point. That's one way of looking at it. It will also enable jobs which otherwise were not possible just with manual labor. So there are many ways robotics makes things much more convenient. There are a lot of steps which require a whole lot of precision, which is not otherwise possible just with manual labor. There are times when you want to lift a lot of load to a very precise location. 5 people trying to manage that load is not going to work, and definitely the precision cannot be achieved. Manufacturing researchers use such robots. Manufacturing researchers help build such robots. So we are on both sides of the table when it comes to robotics. Same can be said for automation. Without building that argument towards automation, I'll quickly jump to the next subtopic, smart manufacturing. How many of you, smartphones all of you have? What does a smart mean in there? Smartphones, right? What's smart about that phone? You can do a lot of things. It also has a way of doing some decision making. That's what makes us smart, because we can take a lot of inputs, come up with decisions based on those inputs. So what smart manufacturing is going to be? So far, everything is broken down into steps. A new design, which means we need a completely new SOP, statement of procedures, or how to proceed, a new set of instructions. Can there be a way to know if there is a new product, how to manufacture it without consulting thousands of experts which otherwise are needed, and their expertise needs to be utilized? Another way to look at smart manufacturing would be, there are a lot of things which are going on in a manufacturing facility. Are we aware of it fully? Each and every inch where what's going on? The way usually such facilities work, it's not possible. A lot of time operations are spread spread over countries. Imagine knowing what's happening in a plant in China, which would affect what's going on right now here in India. However, in today's age, thanks to internet, information can move from one point to another at really, really fast speed, right? It's right at your fingertips. That allows you to make decisions at that speed. Given that you have the capability to get all the inputs, come up with the decision. And this is where smart manufacturing comes into picture, utilizing Internet of Things, utilizing Internet to transfer information at really fast speeds, have algorithms to crack the inputs and come up with solutions which would allow you to work even faster. And then use of AI, artificial intelligence, for better decision making. Next, sustainable manufacturing. We want to earn more profits. We definitely want to be more productive. We want to come up with better products. And someone already introduced the faculty from the climate studies. That takes a toll on the environment. We end up screwing our own future. So, and a big chunk of it is because of manufacturing in some sense, because manufacturing takes in a lot of raw materials and convert it into finished products. How to do that without hurting the environment, or how to do it by hurting the environment lesser in the process. So this is where sustainable manufacturing comes into picture, by reducing the waste and consuming less energy as far as possible. There are definitely better ways to do it, better decisions which can be made when it comes to reducing waste and reducing the energy consumption. A lot of my fellow colleagues here, including some of the work which we are doing in my lab, focuses on some or the other of these, some of the current trends in manufacturing research. When it comes to research, we all have our own ways of looking at it, thinking at it. But when it comes to manufacturing research, any of you, some of you, all of you who would really get enthused today and later times you will spend at IIT Bombay, what can you expect to do? The first thing you can expect is a lot of experimental research. Those of you who have a knack for doing things with their own hands, we have quite a lot of facilities here which would allow you to make those prototypes and learn in the process how the things, the ideas transform from mere ideas to actual shapes and forms. A lot of computational modeling, simulations and predictive analysis. You all have learned complex calculus, algebra. You have learned a lot of many other topics where a lot of equations have been there. Believe me, there are more equations you are going to learn. There is no dearth of those. However, how to use those equations? A lot of time we ask why we learn everything we learn, right? And a lot of those get actually used to conduct these complex simulations and predictive analysis. And we put it all to use in order to understand how some of the manufacturing processes work, in order to understand how some of the complex manufacturing systems work, and be able to take a lot of decisions which will allow us again either to reduce the consumption or to make our production, reduce the energy consumption or to make our production fast or make the whole operation more cost effective. There can be very many objectives to use those equations, what you have learned. Okay. A lot of field studies, I particularly like this one because it allows me to actually connect with the users, the real world, go out and talk to them and see what their problems are. What are some of the places where actual innovation is needed? Some things we do sitting in our lab, knowing there is a need. There are a lot of other venues where we need to reach out to people and understand what their needs are. And connecting to such people and users is one of the essential things to be a good manufacturing researcher. And then definitely, manufacturing in itself is a very multidisciplinary area. However, you always need to reach out to experts from other areas. And that is something which is very, very central when it comes to manufacturing research. We do collaborate with a lot of other experts, and then that makes every experience an extremely learning and enriching experience. So that's another feature of manufacturing research which I thoroughly enjoy. Some of the future trends, what I've talked about in terms of using Internet of Things, actually comes to Industry 4.0. How many of you have heard of this term before? Industrial revolution in some sense was Industry 1.0. A lot of future developments led to Industry 2, 3, and now in the age of Internet, we are at Industry 4.0. You all can be part of that change, given that you embrace what it requires to enable it. Okay. Digital twin technology. A lot of manufacturing processes and systems used to be fairly complex, and it took lot of people to contribute and to understand it. Today, when all the inputs can come in one place, we can, with the help of modeling tools, try to understand a complex system right on one screen. So digital twin allows us to essentially map a full plant, full manufacturing setup in one simple screen. And that gives people very strong foundation to make some very, very critical decisions. A lot of that is happening as we are speaking, and a lot of those who you are going to be interested can become part of those kind of research activities. And then all of that has to be done with a focus on sustainability and circular economy to be able to do things in a way which saves our future, which protects our future. That being said, one last slide quickly. Advanced Manufacturing Processes Lab, that's what I have developed since joining here. All the work is, of course, done with the help of all the students who are part of the lab. This is just the current lot. A lot of those have graduated. What we do, we look at application of robots into the manufacturing. Currently, this robot we are using for doing wire arc additive manufacturing. Additive manufacturing, how many of you have heard of it before? Right? Fairly advanced development where you can bypass a lot of traditional ways of fabricating things. You don't have to machine. The requirement to weld and cast goes down significantly. However, it comes with an inherent challenge. The rate of production is low. Can we go ahead and tackle that challenge and make additive manufacturing a more useful process for a lot many more applications? And this is what we are trying to attempt with this research. There is another research where we are doing friction stir welding or rotary friction welding, and this research focuses on joining two different materials. In today's automotive, aerospace, marine, any industry you name, we want to produce lighter yet strong parts. How to do it? Use two different materials, be able to join them. But when you try to join two different materials, it's extremely challenging. We develop processes, we focus on developing recipes to join such materials. And we have developed such joints for various industries since we have been doing work in this area. So without developing too much, we'll thank you for your attention and looking forward to any questions.